Good morning, one and all. I am Dr. Ramya Swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is application to continuous beam with and without settlement of supports. So, as a part of slope deflection method, we are going to understand in this particular chapter how we are applying this slope deflection method, what are the various steps involved. So like this, we are understand these and applying continuous beam with and without settlement of the support. Here the problem, analysis the continuous beam shown in figure. As shown in figure, this continuous beam has 4 supports. Those are A and D are fixed ones, B and C are simply supported ones. So according to this, we are going to calculate the moments and the required things using this slope deflection method. So the support B settlements by 10 mm and with and without settlements, if settlement is there, that is 10 mm, and take E is equal to 2 into 10 to the power of 5 Newton per mm square, and I is equal to 16 into 10 to the power of 7 m the power of square, and sketch these shear force and bending moment diagrams. So here, so the based on that, this is equal to A, B, C, D are the supports. And A and D are fixed supports. Fixed ones. From A to B, the distance between the beam length is equal to 6 meters. From B to C, that is equal to 3 meters. And C to D is equal to 6 meters. And here, from A to C means A to B and B to C, the loading condition is UDL, that is uniformly distributed load. From C to D, that is point load. C to D, that is point load. So here A to D is there, in that from A to B and B to C, that is uniformly distributed load. From C to D, that is equal to point load, that to a mid of the C to D. Now find out the fixed end moments. So according to the supports and loading conditions, we are going to calculate these fixed end moments. So the fixed end moments at A to B is equal to minus WL square by 12. So W is equal to 20, L is equal to 6 square by 12, that is equal to minus 60 kilonewton meter. The fixed end moment from B to A is equal to plus WL square by 12, 20 into 6 square by 12, that is equal to 60 kilonewton meter. Now fixed end moment for B to C is equal to, it is a point uniformly distributed load, so WL square by 12. So 20 into 3 square by 12, that is equal to minus 15 kilonewton meter. For the similarly fixed end moment from C to B is equal to plus WL square by 12, that is equal to plus 15 kilonewton meter. In this, the CD is in different kind of loading condition when compared to the A to C. So the fixed end moment for CD is equal to minus WL by 8, that is equal to minus 50 into 6 by 8, that is equal to minus 37.5 kilonewton meter. Similarly, the fixed end moment for DC is equal to WL by 8, that is equal to 37.5 kilonewton meter. So like this, we are finding the fixed end moment based on the loading condition as well as the type of support type. So we calculate these fixed end moments. Now the slope deflection equation. So according to that, we are identifying the slope deflection equations for MAB is equal to the fixed end moment for moment is equal plus 2EI by 6 2 theta A plus theta B plus 3 delta by L. So, and substitute, finally we'll get one equation. Similarly, for MBA, so the fixed end moment plus the slope deflection equations, and we'll get the equation. Similarly, for the all moment equation, all the support system MBC, MCB and MCD within the same pattern, and we are getting the equations. And the next step as a part of slope deflection, joint equilibrium equations. So at joint B, the equilibrium equation is equal to MBA plus MBC. Substitute those two equations. Finally, we will get EA by 3, 6 theta B plus 2 theta C plus 3 by 200. So that gives minus 135. Now at joint C, so this is for joint B. Now moving for the joint C, that is equal to MCB plus MCD is equal to 0. So EI theta B plus 3 theta C plus 1 by 100, that is equal to 33.75. So equating these two, we'll get the theta C is equal to minus 1 by 464 and theta B and theta A is equal, theta B is equal to minus 1 by 402 and theta C is equal to minus 1 by 464. We'll get from these joint equilibrium and done by the all the calculation that gives this one. Now these are the final movements what we get from moment with respect to AB is equal to minus 139.843 kilonewton meter and MBA is equal to minus 46.354 kilonewton meter. For similarly, for this moment, these slope deflection equation, the final moments for these MBC and MCB as well as the CD and DC at there. So these are the final moments. Now here we are going to draw and understand about the shear force diagram. So draw the shear force diagram. Considering this span. So the span AB, from span A to B, we know the uniformly distributed load 20 kilonewton per meter square is there. After done with calculations, MA is equal to 139.84 kilonewton meter. MA is equal to MBA is equal to 46.35 kilonewton meter. In between from 6 is equal to 6 meters. From A to B is 6 meters. Now taking the moments from A. Taking moments from A for to draw the shear force diagram. Now that from taking moments from A means, so 20 into this is 6 length. So 20 into 6 square by 2 and this is like this and this is this indicates the negative sign. So minus 46.35 and also this is there for this minus, this is also indicates minus. So this this is the thing what we are going to understand, that is equal to this is anti-clockwise. So anti-clockwise is negative. So this anti-clockwise, so minus and minus now are, and these the reactions like this. So this is the reactions what we get from this. This is also anti-RB1 is equal to into 6. So this is equal to full. And from here to here, this is equal to anti-minus RB1 is equal to, this is the 29.97. Now from reaction RA is equal to 20 into 6 minus 28.97. This RA is equal to 91.03 kilonewton. Similarly, the first one RB1 is equal to 28.97 kilonewtons after done the all the calculations. After done all the calculation, we get the reactions for A and the reactions for B. So 20 into 6 square by 2 minus 139.84 minus 46.35 minus RB into 6. Now RA is equal to 20 into 6 minus RA plus RB is equal to 20. From this we calculated already. RB is equal to 29.97. Substitute this. Finally we will get RA. Like this we find out the reactions for the support, for the span, whichever the span we require. Now here for this span BC, this is the equations what we get, that is equal to RB2 and this is RC1. Oh, in between that is equal to uniformly distributed load. This RCMCB is equal to there, MBC is also there. Now taking the moments about B. Now 20 into this length is 3 meters. So 3 square by 2 plus this is clockwise is positive. So now 83.35, here also this is clockwise. Clockwise is positive plus 46.3 minus this is RC1, this is anti-clockwise, minus RC1 into 3 is equal to 0. We'll get RC1 is equal to 7. After done the calculation, this is the value what we get for the reaction at C. Now RB2 is equal to RB1 plus RB2. RC1 RB2 is equal to 20 into 3 minus 73.22. Similarly for RA is equal to 20 into 6. This is equal to RB2 plus RC1 is equal to 20 into 3. So we know RC1 already, find out the RB2. Finally, we'll get these reactions for both the sides. Now consider the span CD. So in this CD, this is different for this point load and that was at midpoint. This is 3 meters and this is 3 meters. This R. MCD is equal to 83.48 and this is also 14.5. 11 kilonewton meter. This is 50 kilonewton point load. Till the previous, those are all uniformly distributed load. This is the point load. Taking the moments from C, taking the moment about C. Now this 14.55 plus 50 into 3 minus 83.4 minus RD into 6. This clockwise is positive and this anti-clockwise is negative. This is clockwise positive and this is anti-clockwise negative. So finally, after done all the calculations, what we get, this RD is equal to 36.5 kilonewtons. So draw the free bending moment diagram. So till this is the shear force calculations. Now move on to the free body diagram. This AB is equal to WL square by 8. MBC is equal to WL square by 8 and MCD is equal to WL by 4. So here that is equal to L is 20. So that way this is 90 and here L is equal to 3. That is equal to 22.5 kilonewton meter. Here that is equal to 75 kilonewton meter. Like this we are going to calculate these slope or shear force as well as the, once we got these final equations from the from the step by step procedure, find out the fixed end moments, slope deflection equations. According to the joint equilibrium conditions, we identify the final moments. From that, draw the shear force and bending moment diagrams. For that, we are calculate the reactions which are involved. And finally, the bending moment diagram. So, draw this shear force as well as the bending moment diagrams. According to this, we have to understand how to draw the shear force and bending moment diagram. So the shear force diagram we know. According to that, this is 19.1. This is A and B and C and D. Now this is the thing which what we understand, that is equal to it will be in between C, and this is CD. This is CD, positive and negative. From here to here, that is different. From here to here, that is different. So like this, we are going to draw the shear force diagram. Similarly, draw the bending moment diagram and shear force diagram. Like this, we are going to understand these various conditions which are going to for these continuous beams. Like this, we may understand various numerical values also. This is the procedure for draw the bending moment and shear force diagram. So these are the some of the references we may refer for the getting the various examples which we are going to consider thing for the slope deflection method. Thank you. We will see in our next class.
Like, share and subscribe. Hit the bell icon for more updates.